Whatever. Yes, it's a great pleasure to welcome here Dimos Kazanas. I'll say a few words about Dimos. Dimos did his bachelor's from the University of Thessaloniki, the physics department there. Then he went to University of Chicago, where he did his PhD. And then his first postdoc was at the Goddard Space Flight Center, Maryland, then the University of Maryland. And then 1988, he became faculty at the Goddard Space Flight Center, where he stayed there. He's been there now for almost 40 years, right?
Since I started as a
Yes,
postdoc
as a faculty.
with the government 37.
Right, okay, fair enough. Dimos has made contributions to a vast area of astrophysics, but also theoretical physics. He's going to talk to us about gravity beyond Einstein. I'm very, very privileged working with him, not on gravity issues, but on theory of continuum emission from AGN, active galactic nuclei, and whatever could be happening over there. I will just want to point out one of the most major, but a little bit, say, not well known, right, contribution of Dimos to theoretical physics, and that was the idea of inflation. Dimos' paper was published before Booth's paper, right? Okay, it didn't have the catchy title of inflation. It was vacuum public, right? Which I think was very catchy,
Oh.
but still, you know, the idea is the same, and it was published before, as I say, Booth's paper. Anyway, Dimos, without me delaying you anymore, please.
Okay. Thank you very
come up
much,
and,
Sifu. And
start your
I'm
talk.
very happy to be back at the University of Crete and seeing old friends and well, some new people here that I haven't met before. Costas for the first time. I've known Vaso from from my past life in the United States. So here is the title of the talk, and I think well, how many people are involved in high energy here, or were involved? Okay. Well, I'll have something for everybody a little bit. Something for high energy people, some people who work in gravity, some for people that work in star formation. And believe it or not, it appears after what I'm going to say that the effects of gravity, of theory of gravity, appear in all scales. So here are the some of my collaborators from 30 years. One is Philip Mannheim, University of Connecticut. Joseph Sultana was University of Malta. Dimitris Christodoulou of UMass at Lowell, retired recently. And Dimitris Papadopoulos, who was at the University of Thessaloniki, he's emeritus now. So here's a bit of an outline. I think I mentioned that last time, well, maybe 30 years ago I was here, or 20 years ago I was here. About conformal gravity, that's some work was done with Philip Mannheim. And the origin of inertial masses, why is the inertial mass equal to gravitational mass, is called the equivalence principle. We don't have an answer to that, but I'll show that there may be a relation to that. And because these equations are fourth order, we have with Dimitris Christodoulou a second order approach to those equations, totally phenomenological, and hopefully somebody will give me new ideas, or I'll give you some ideas that you work on your own. So let me just start from some general considerations. In the absence of the Newton's constant G, there is no way of forming a combination of physical constants that produces a mass. So mass and gravity are therefore interconnected. We get some mass from G. On the other hand, we know that masses are also from the Higgs mechanism. That's not my field. I understand things kind of qualitatively, and if there is any suggestion from the audience, I will be more than happy to entertain them and correct my my prejudices. So the current theory of gravity, of course, is the general relativity, and that is derived from the Hilbert-Einstein action, and that is basically the integral of the Ricci scalar. We know the idea of Einstein was that gravity is related to geometry, and we had the geometry is given by the Riemann tensor with the contractions of that, and it turns out that the this expression, the Ricci scalar, if we take the functional derivative of that, gives us the Einstein tensor, and the Einstein tensor set equal to the energy momentum tensor. That gives us the Einstein equations for a given distribution of matter. 1 over g comes into these equations, and that is basically what gives the mass in there, and the corresponding mass is the Planck mass, which is the square of 1 over g in units where h bar equals c, so equals 1. And those are the units we use for quantum problems. And well, in those units, the gravity comes with a scale. Now, my understanding is that gravity, along with it's along among all theories of fundamental interactions in the case that the quantity that's in front of its action has dimensions. The other interactions have dimensionless quantities, and that apparently is fundamental in being able to do quantum corrections in terms of loops. And the only one that, of course, is not defined by a local invariance principle. I'll say a few things that I understand, not in great depth, but I'll repeat what I think I understand. So can we try a local invariance principle for gravity? And the question is which one? Well, we can get what Mannheim's background was actually high energy physics, so I was just learning things from him. We decided to basically put scale invariance at the conformal stretch of the geometry. You take the geometry and you put a stretching factor which depends on the coordinates, and you got a different value of the metric tensor. And the question is here, oops. Let me see if no, right. So can we gauge the local symmetry? One can gauge any symmetry effectively. That's what we learned from Weil. Weil wanted to actually use local invariance. Again, this particular invariance, the scale invariance, and he realized that he realized that you can do that by changing the definition of covariant derivative. And this thing has been moved into the quantum physics regime by changing the phase of the wave function by adding a factor which depends now on depends on space of position. And it turns out that as far as I understand, that for people that do the quantum field theory, then the derivative, we have the covariant derivative, gauge covariant derivative. Instead of the partial derivative, we have basically something that came out a vector field, which is called that's the electromagnetic potential. And that's how you can do the same thing for all fundamental interactions, and for strong interactions. If as I understand, then this becomes a non-abelian, more complicated vector field there. I'm not going to talk about that. Anyone? So in this particular case, with the scale invariance, instead of having these issues that this fields that come from changing the phase of the wave function, we have simply something that involves the stretching of the geometry, omega. And if anybody knows a little bit of gravitational theory, then you know that the covariant derivative involves what's called the Christoffel symbols, which are partial derivatives of G mu nu. And if you change the definition of partial derivative from this to this, then the original gammas, they get additional derivatives of omega. The omega nu means essentially the derivative of omega with respect to index nu. It turns out there's a combination of the Riemann, Ricci, and Riemann tensor, Ricci tensor, and Ricci scalar, which actually all those quantities depend on gammas and derivatives of gammas and multiplications of gammas. You don't need to know all the details. However, there is a combination which is called the Weil tensor, which is independent of any omega you put in there. So you can make a stretch of the geometry. This becomes very complicated. The gammas are already complicated, and you add all these things. And if you take the proper combination of this, this, and this, you end up with a tensor that has 4 indices, of which all the omega mu's cancel, and that is called the Weil tensor. And it turns out that if you get the Lagrangian, which is the square of the Weil tensor, that is, when you make a stretch in the geometry, this takes several values of omega outside of it. This and that the inverse number of omegas, and it turns out that this quantity is independent of the omega. That's the Lagrangian we try to do, and this can be simplified to look like this. It's the Ricci tensor square minus the Ricci scalar, a third of the Ricci scalar square, and you basically try to write new equations for the gravitational field. It's given in this reference, and it gets complicated. In tensor form, they look like this. This piece comes from the R mu nu square, and this piece comes from the R alpha alpha square, and the total thing is the total gravitational tensor, which replaces the Einstein tensor of general relativity, and of course T mu nu is the stress energy momentum tensor for matter we put on the right on the other side, and those are complicated to compute. And it turns out back in those days, these days I think they're computer programs that give you directly the answer. But at that time, back in 1990, we only had symbolic manipulations that could do derivatives. So you write the equations for this action. Okay, let me back off once. You write a metric that has this dt component, the AR component for static spherical symmetric problem. There's no time anywhere in here, and if you set c equal to r squared and d equal to r squared sine squared theta, this is now as the metric of the static spherical symmetric problem, and whose solution in general relativity is the Schwarzschild solution. It turns out when you instead of doing so, in order to write the equations, basically you take the Lagrange equations, which are these, and go up to the second derivative. So those are now functions r squared and r squared sine theta. We only have a and b unknown, and you can see that you have basically higher derivatives of b and higher derivatives of a. It turns out quickly, you don't have to worry too much about this, that conformal invariance allows you to set a equal to 1 over b. In Einstein theory, when you're in the vacuum, you can set a equal to 1 over b. In this case, you have an additional degree of freedom, conformal invariance, and then under those conditions, you can set a equal to b in the previous equation, and you get something which is much, much simpler. It still has 4 derivatives. I'm sorry, this one is the RR, has only 3 derivatives. And you can integrate that, and turns out there is an exact solution, and you have 3 integration constants. In Einstein case, you have turns out there are only one integration constant, and that's C over R, and you find that this quantity has to give at large distance has to be the Newtonian potential, and therefore that quantity here is 2gm over R. In this case, we don't know what it is. We have 3 integration constants, beta, gamma, and K. And it turns out that the formal general gravitational tensor, if you make this stretching, then the gravitational tensor, the omega comes outside of this. So there's no derivatives of omega. Omega is, in some sense, gauge for this theory. So now we understand what's going on here from the solution, at least. We understand that the 1 over R term, those are constants. It's 1 over R, that's the Schwarzschild piece. And we understand the KR squared term, that's the de Sitter term. And if we have a Schwarzschild de Sitter static spherical symmetric solution with some cosmological constant, in Einstein we have gravity have 1 minus this component minus that component. Out here we have this other piece, which is a constant term, and a term that depends on R. It's linear on R. There's a potential which is linear on R, and that actually looks like the quark potential. That's my understanding, that people, in order to explain the high energy experiments in strong interactions, they assume that there's a potential linear between the quarks. The interesting thing with this thing is that this term is certainly cosmological. It has to do with the cosmological constant. We don't know this value. However, from observations, we know that it's the KR squared term is roughly 1 over our Hubble square. And the question is, what about this term? And it's asymptotically non-flat. The guess is that it's also of order 1 over our Hubble. And then we ask the next question to ask is, when do these terms are comparable with that? We understand this term is the Newtonian. Well, we don't know what beta is as such, but we believe it's the Schwarzschild radius. Beta is the Schwarzschild radius. So these 2 terms will become comparable when the Schwarzschild radius over R, which is this, is equal to R over our Hubble, or when R squared is proportional to the geometric mean between the Schwarzschild radius and the Hubble radius. The interesting thing, of course, with that is that the Hubble radius depends on the history of the universe, now has a value, which is basically the speed of light times the age of the universe. At an earlier time in the universe, it was the age of the universe was smaller, and therefore our Hubble was smaller. And that's something that people who do observation may have something to say about that. Or you can write as a M over R. It reminds me, I should set my phone. And that's a column density. It's a column density which is comparable to as this is roughly the column density of the universe, if you like. The characteristic scale for galaxies, where these 2 are the same, is approximately 10 kiloparsecs. So we thought that this has to do with the galactic with the dynamics of the galaxies. So we can here are some more general considerations. We set beta equal to 0, then you have basically 1 minus plus gamma minus KR square. It turns out there is some coordinate transformation we can make, and the metric now becomes inferior to the curly brackets, looks like the Robertson-Walker method. This factor is outside. Anything that's outside is a conformal factor, and if the theory is conformal invariant, this presumably is not necessarily relevant. Well, that's something I don't quite understand very well, but the important thing is that this piece is like a Robertson-Walker with spatial curvatures, space, which is proportional to gamma squared over 16 plus k over 4. So this, in some sense, justifies the consideration of gamma as a component that has a cosmological importance, large-scale importance, and it may not be unreasonable to set it equal to the inverse Hubble radius. With that, we basically sat down and calculated a rotation curve of a galaxy. Usually, galaxies are thin disks. Well, not the spiral galaxies are thin disks with an exponential distribution of matter. And here is basically, so with this, we know how much mass is inside a given radius. We can calculate the gravitational force. We set it equal to this square over r, which is centrifugal force. We can calculate the velocity. And with this exponential distribution, if we didn't have any dark matter, this would, as a peak at around 2.2 R0. However, if we add now the linear term, and we add the two together, then we find something which, well, this is the curve we get, but it's close enough to flat up to for this particular galaxy, which is NGC 3198. These observations are now observations in H1. And because it's H1, you can have big telescopes and you can basically see the hydrogen transition the large distances. And therefore, we have observations now that go all the way to roughly 10 times R0. Usually, optical observations stop around here. It's too faint to go a few times beyond R0. And therefore, but in H1, we can see it. And now we know that the rotation curves are flat. And here's a number of galaxies we try to really fit that way. These galaxies, for those people who do galaxy dynamics, are dominated by gas. And this is the stellar contribution. And this is the gas contribution. Well, we have deviations here. There's nothing I can do about that. Those galaxies are dominated by gas. And those are dominated by stars. This is the very little gas here. This is the stellar contribution. Stellar contribution, the linear term. Stellar contribution, the linear term. And you have to bear in mind that the linear term, they all have the same normalization. So the stellar contribution we get by observations of the stars, but the linear contribution is R divided by R Hubble, the local R Hubble we have now. The fit are decent. I'm sure that if you are willing to put more parameters, you can fit. There is deviations usually at large distances where the data is not terribly good. So this relation now, so from equality of this to the linear and the Newtonian term, we have a relation between R and mass. We assume this is constant. Because the systems we believe they're in virial equilibrium, we have an additional relation. It tells you the velocity square is proportional to gm over r. Between this and this relation, we can eliminate r, and we have a relation that relates the velocity, because that's measurable, to the mass of the galaxy. And we find that the velocity goes like the mass goes like the velocity to the fourth. don't measure the mass, we measure the absolute magnitude of the galaxy, and we assume there's a relation between luminous matter and stellar mass, factor of 7, I think it's called mass to light ratio. And so this is the mass so estimated, and it's proportional v to the 4. This is known as a Tully Fisher for the spiral galaxies and Faber-Jackson relation for the elliptical galaxies. And extends over 7 decades in radius or 14 decades in mass. So here's the Faber-Jackson relation I took from Wikipedia. I used the mass to light ratio factor of 7. So I shifted this by a factor of 7 in mass to go from magnitude to mass. And we have a similar relation. We're Okay. So here the normalization for Larson. Take GM over R squared equals CH naught.
No, 1 second. Why? No, but because he's.
No, that's here.
But his mute is.
Hmm.
No, it's not.
Maybe I should.
Maybe here.
Newton will be here.
Okay, no, it's okay.
Now I'm okay, all right. So just for the normalization, GM over R squared equals CH naught, and V squared equals GM over R, and this H naught is somewhere here, but for 1 kilometer per second is 100 solar masses, for 100 kilometers per second is 10 to the 10 solar masses up here. For 100 kilometers per second, 10 to the 10 solar masses. And this extrapolates into that. This is a different relation that's called the M sigma relation for the black holes of galaxies. So if you have the mass of the galaxy, then you can, from this relation, calculate the mass of the black hole that's at the center. It has slightly different dependence on sigma. That indicates that the given fraction of the mass of the galaxy is basically been accreted to grow the black hole so that it obeys the same relation. That's something totally different that was shown up by Merritt and so we go to a little bit just put more powers of mass and radius up here. It seems that, well, the protostellar nebulae, that's the Larson relation. Those are the globular clusters. These are all schematic drawn by hand. I mean, they put all the data would be roughly out here. We have a certain dispersion, galaxies and classes of galaxies. The visualized system seems to be on this general M proportional to R square line. And the black holes, of course, are in R equals M line. And the universe is within its own Schwarzschild radius. So the universe actually is the intersection of these two different curves. I don't know what it means, but I'm telling you so that some of you may have some great ideas of what that might mean, and you write some very interesting papers in the future. Now with a fantastic extrapolation to the mass of the electron, this passes through the radius of the not the Compton wavelength, but the classical electron radius. Again, without this, I wouldn't have to sit down to calculate what's the column density of the electron and to find out that's close to the column density of the universe. Is that important? I don't know, but it's kind of strange, if nothing else. We have a solution with charge in relativity that's called the Rice-Nostrum solution. The nice thing about the electromagnetic tensor is that the theory is conformal invariant, so we have conformal gravity, conformal invariant gravity, and ENM, which is also conformal invariant. The TRR is this component of the energy momentum tensor is proportional to Q squared over R to the 4. And it turns out with this source, you can solve again the equations exactly. And this is what we had before. We add now this term, which is Q divided by alpha. Alpha is the constant dimensionless parameter in front of in the gravitational action. It has to divide the Q unit of that. Its component of this metric tensor has to be dimensionless. In this particular case, this is Schwarzschild radius divided by R is dimensionless. Out here we have Q, which is dimensionless by itself. So somehow we have to make dimensionless the denominator, and you make that with the gamma. So interestingly enough, because of the dimensionality of the equations, the charge contribution to the geometry has the same functional form as that of the mass. In Einstein theory, Q squared is multiplied by G, and G has dimensionless of 1 of length square, and therefore you have to have r squared in the denominator to make the whole thing dimensionless. And that was called the Rice-Nordstrom solution. So there's no way in any theory with charge that this theory will end up with Einstein. That's something to bear in mind. Okay. The Newtonian limit, it turns out if you look at both the RR component, the 0, component, they more or less have the same dependencies. Here is the 1 over r to the 4, 1 over r to the 4. If you take this combination, the only thing that's left is the fourth derivative of b times third derivative of 4 times third derivative over r, and this operator is del 4b. It's a linear operator, even though all those are highly nonlinear. And the Green's function of this operator is r minus r prime. In Newtonian theory, the Green's function is 1 over r minus r prime, and then you can integrate over a distribution, and you get that basically you add more delta functions, you get the Newtonian potential of a spherical symmetric distribution that goes like 1 over r. Here we get r minus r prime, and we have to integrate over some distribution again. And if you do the integral of the angular integral here, as you do in Jackson, you find out this combination, and you have now again what you do in electromagnetism. You take from 0 to r, this integral from 0 to r, and from r to capital R, and you have now a term which is linear, and term is 1 over r. So even though the gravitational, the Green's function is proportional to r effectively, you still get by integrating over a distribution, you get a component that is 1 over r. The integral of from r to the outer limit is proportional to r squared, which means the geometry interior to a spherical shell is proportional to kr squared. In Einstein theory, Newtonian theory, interior to a shell, we have basically Minkowski space. So that's something just basically to have in mind, which means now that the sources of this theory, they're not delta functions, they have to be derivatives of delta functions, because if you put a delta function here, delta over r squared, it will give you 0. So you have to put the second derivative of delta function times r to the 4 integral, I'll give you something finite. So what we come out from all these things that its source, of this theory, has to have 2 parameters. One that gives you the Newtonian term, one that gives you the linear term, which is only a second order moment. Those are mathematical issues. Let me go quickly through all that. The point is, if we want to make contact with observations, we still are tied to G. Now, in this case, there's no G theory. So what do we do about that? And well, I'm open to suggestions here, but what I personally did, out of the Lagrangian, I pull out an R alpha alpha, because this is the action of the Einstein action, and therefore this quantity here plays the role of 1 over G. We have the exact solution of the full theory, so therefore this is roughly equal to the Planck mass, if you want to interpret this geometric component as an effective 1 over G. We have the exact solution of the full theory. We can calculate this now in the full theory, and it turns out that this vanishes when r goes like, actually error here, square root of G over beta. So near the black hole, if you go near the black hole at some distance r, which is square root of b, we call ISCO or something if you like, or the stable photon orbit, the 1 over G becomes infinity, or the Planck mass goes to 0, and naturally you expect that to have quantum effects that will be dominant, because the reason we don't see the quantum effects now is because the quantum scale of gravity is 10 to the 19 GeV. But if the effective Planck mass goes near zero, there should be quantum effects right at the near the horizon of the black hole. So let's go to some additional considerations with respect to that. As I said in the very beginning, there's no way to form a combination of physical constants. Nowadays, we know that the masses, of course, are results of the spontaneous symmetry break-in, with the Higgs mechanism as basically providing all the masses. And what we have a scalar field, which is called this Higgs field, phi, a kinetic energy minus a potential energy, and that is basically as a m phi square plus lambda phi to the 4. And depending on energy, the expectation value of phi is close to zero when it's dominated by this term. And when it's dominated by that term, then we have this double well potential. Let me just, I think I have a, no, I don't have a copy of that. The interesting thing, of course, with the scalar field, that I don't quite understand all these things in great detail. When you do loop corrections, because the loop is not corrected to anything outside, you can basically send the momentum, which is given by k, to infinity. And they have integrals of this form. And because there's a mass down in the denominator, when you send to k to infinity, you get something that contribution is proportional to the cutoff of the theory. The theory, we think that the cutoff is the Planck mass, and therefore that actually causes a problem. There should be some cosmological constant which is comparable to the Planck mass. We don't see that, which means there must be some very fine cancellations of this diagram from another component. And if I understand correctly, this is called a hierarchy problem. Here's a piece of a paper by conformal symmetry in the standard model. Conformal symmetry is broken only by the explicit mass term for that's in the standard model, no gravity here. Explicit mass term on the scalar field. If we insist on conformal invariance, then we have to change this potential. This term remains the same, but this component now has, in order to be conformally invariant, instead of the mass of the Higgs as the richest scalar with a minus 1/6 term in front of it. This is 1/length square, so it has the same dimensions as the mass. Of course, so this term plays the role of the mass of the Higgs. And immediately you say, how is that possible? I mean, how do we calculate the mass, the scalar curvature, or use Einstein's equation? Einstein's equation with the Einstein tensor, it's of the same order as alpha. Alpha is 8 pi g rho. G is 1/the Planck mass square. Rho is, as dimension, the Higgs mass to the 4th power. So we take 2 powers of the Higgs divided by m Planck square times the m Higgs square. This is much, much smaller than the mass of the Higgs. So if you think in terms of Einstein, there's no way to have a conformally invariant theory for the standard model. However, in conformal gravity, the gravitational tensor is proportional to R alpha squared. And that has this 1/alpha in front, which is of order m Higgs to the 4th power. And therefore, there's no take the square root of that, and therefore R alpha, it can be of order m Higgs squared. So in purely fourth order theory, there should be gravitational effects at the LHC. This has been discussed before. That was my friends Savas Dimopoulos and Arhani Hamed. They tried to basically make the gravity is very, very strong near the at these energy scales by insisting that there are additional extra dimensions. So the gravitational potential, instead of 1 over r, becomes 1 over r to the 7th, and therefore by the time you go to the Higgs mass, then gravity is also strong. Here gravity becomes strong because g varies with energy. So this is a claim that I thought it was correct. I asked the relativists and they couldn't tell me if that's correct or not. That in conformal invariant theory, because conformal transformations do not change the conformal structure of the universe, if you start without black holes, you shouldn't be able to produce black holes. I don't know if that's true or not. And therefore, what's the interior of a black hole? That should be the unbroken Higgs mass. I'm repeating all these things. As I said, people try to do the same thing, having gravity strong at the LHC, so they can avoid the hierarchy problem by having extra dimensions. It turns out that in cosmic rays, we see some effects at energy scales which are close to the mass of the Higgs at the center of mass. It's called the knee of the cosmic ray spectrum. I don't know if it's related to issues that happen, quantum gravity issues at the LHC, but for whatever it's worth, my friend Argyris, Fred Argyris, Nicole Argyris, passed away last year. We used this issue of energy flowing out from the brain to the bulk and causing this break. I don't know if that's true or not, but there is missing energy at LHC. That's my understanding. Higgs going to Z going to neutrinos, and they observed is 0.26 of this, and the expected is 0.17. So besides this ratio with this transition, we also have maybe energy lost in gravitational waves of very high frequency. As I said, all those are okay, fine. Those are only conjectural issues, but gravity. I will skip the gravitational lensing. That they don't seem to affect. Let me see. And one last thing that I have is I'll skip that too. We can discuss that in private. So as I said, we in order to understand anything like the theory I discussed, we need to have a G. And the G, of course, is given by God in relativity, and is not allowed to be varying. On the other hand, we have indication that there is something that changes as a function when the acceleration drops below a given value. That's what this gentleman here mentioned, Mond. That's what the indication was from the earlier discussion with the galactic dynamics. When you go far away from the gravitative mass and the acceleration, the gravitational acceleration becomes small, then you have the linear term, which is a constant acceleration, basically, that takes over and makes the galactic rotation flat. With Dimitri here, we decided to make the G a function of the acceleration. You can do that, and basically you can, so let me go back once. So the idea is that when we have this characteristic acceleration, when A is much larger than that, then we have G, standard G we know, which is Gm over R, the Newtonian G. If you start dropping, if your acceleration, the Gm over R becomes much smaller than A naught, then the effective G increases, and that's what makes the galactic rotations flat. Totally phenomenological, but if we don't know anything else, that should be good enough until we find something which is more fundamental. So basically, that's what happened. For large accelerations, greater than a naught, we have a naught plus some small correction. Very small accelerations, this expression we got, I gave you earlier, gives you basically an acceleration, which is the geometric mean between the Newtonian and a naught. That's what we have actually for the conformal gravity and that's what Milgram uses in Mond. So I'll basically go quickly through all my whatever I discussed so far. The most observationally direct conclusion of what I said is this mounting, I would say quite a bit of mounting evidence for the presence of a characteristic acceleration of the universe, which is of the age of the order of CH naught. It turns out that for cosmology, we need to put dark energy when the acceleration drops below CH naught. So we have now things that happen at galactic scale when you have basically a Weyl tensor, which is non-zero because you have a central mass that attracts objects. And we need to add an acceleration to explain Newtonian dynamics there. And for something which is homogeneous and isotropic, we need to add another component called the dark energy. And again, that appears at late stages of the universe when the acceleration basically has dropped below a characteristic value. So if there's anything to get out of all that is that observations appear to indicate there is a characteristic acceleration in the universe. Whether this theory is right or wrong, or any of what I said here is right or wrong, there seems to be this case. It's of interest that this occurs as a solution of the fourth order equation, which at the beginning that we started, we had absolutely no indication that we had no goal to explain this effect. That's why I kind of like it, because if you get things that you don't looking for and you come up with, then they're more interesting. And we said I have more appreciation, and I like to believe in those things more than if I really try to find a theory that gives me exactly what I really look for, although those are reasonable and ways of pursuing the research. The thing that's big that we need to understand, at least I need to understand, is Newton's constants, which is absent in purely fourth order theory. What is that? And is it variable? Conformal symmetry begs the issue of mass generation. Such symmetry naturally connects the microscale with the macroscales and puts gravity effects into the laboratory. A universe that begins close to conformal invariant state, no black holes. Is it possible to produce black holes? Maybe not. Hawking at the very end of his life claimed that the horizons we see, they're only apparent horizons in some kind of strict mathematical sense that he understands and I necessarily don't. If the horizons are only apparent, there's no black hole evaporation, because black hole evaporation requires real horizons. And therefore, we resolve this issue of what happens with a black hole evaporation with a loss of unitarity. And I think I'll stop here. Thank you. Yes.
I'd like to make a comment, which I should have.
By all means.
I should have probably done. The C-square theory, the Weyl tensor square theory, is highly problematical, and I'm
Understand.
Well, but then
You mean the ghosts? Is that what you mean?
Stability or ghost, it's the same thing.
Yes.
So
yes.
Anything you did based on it is highly suspect.
Well, I'll refer you to a paper by Mannheim and Benter that claim that they resolve the issue.
That's
of ghosts.
a nonsense claim anyway. There's also
Okay,
a claim by Lee and Wick. These claims tend to work to low order, but not at higher orders. And you cannot get out of the fact that a fourth order system needs two canonical pairs instead of one to do classical or quantum mechanics on it. And as a result, it has an unbounded, unstable kinetic energy.
okay, yes,
Just do the Hamiltonian dynamics of it. You cannot get out of this. In this case, in your case, which is C squared, you could also have added an R squared term and not disturb scale invariance. You would end up with a theory,
R squared,
R squared, yeah.
yes, okay,
Yes, but that's not the problem. Both of them have a problem. What happens in the end is you have the zero energy theorem of Horowitz and Strominger and
Yes.
someone else that starts from B. It's
Right.
three authors, mid-date this paper, or no, maybe a little bit later. And
midday, yes,
yeah, and so you have zero energy. But the instability, what it tells you is that you can have an incredibly very fast, a very huge ensemble of particles with negative, they go downwards, and another one with positive, and they sum to zero.
I see.
So you cannot have a mostly empty universe, which is what we observe. End of story. Whatever you derive based, I mean, I couldn't follow your.
Yeah, sure, I mean, it's not an issue following, no, it's
I
not
don't
quantum,
know-
there's no
I don't
quantum
know
stuff.
where you use that theory, but to be honest, I got this message and I was curious to see what you would do with the problem of the C-square theory. I thought you would somehow magically do something.
Yes, no, I was not planning to provide a resolution to that. I referred to the Bender and Mannheim, or Mannheim and Bender. I don't claim to understand those, their arguments. However, in electromagnetism, if we add radiation reaction, we also have unstable solutions, and somehow nature doesn't seem to care about those. So it chooses the secondary ones. Issue has to be resolved. I agree with you. The issue has to be resolved.
Well, I think it has been resolved.
It has been resolved.
And they are unstable. What's wrong with that?
I don't know.
At any rate, you would have to break the conformal invariance, otherwise you would never get a mass.
Yes,
And I don't.
today,
Maybe I didn't, you said it, how did you get a mass out of this?
out of the,
You started with a.
it's an integration constant there. We don't know what.
No, but you have to break the symmetry. What integration constant? How did you break the symmetry to get a mass?
Well,
Volume
when I
variance-
solve the vacuum, then I don't break the symmetry. It's the vacuum solution, and I get an integration.
So what mass came out? What's the?
Oh, well, we don't know. In order to do that, you have to put a no-vacuum solution next to it, and you get, the only one I could figure is the Q, the charge. And we have the solution with the charge, and I don't have anything else than that. So, but the same is true with Einstein. When you solve the Schwarzschild solution, you have a vacuum solution, you have something which asymptotically you say it must be the,
It's the test point mass.
yes, that's right,
And it's a solution, but not at the source,
not at the source.
away from the source.
Yes, that's correct. And if you don't, you can do the interior problem for Schwarzschild. If you have a constant density, spherically symmetric, then you can show that the integral of that mass without a square root of g in there, the flat integral is the coefficient of 1/r, and therefore you relate the I think that's in Weinberg book. You relate now the mass of the object with the geometry outside of it. Out here, I don't have something. Well, I suspect I have to use a conformal invariant Tim, you knew, that's why I use electromagnetism. Now, in reality, of course, we have to use something else, but is it true that something else, do we really have black holes? Or if the theory is conformal invariant, no, never mind the problems you suggest that are there, and I don't have an answer to them. Do they really get infinite densities there, or as they say, if you fall into a black hole, you spaghettify it, or you melt as you approach the horizon because somehow the symmetry is restored near the. A conformal theory knows about the horizon, so you cannot just willy-nilly cross the horizon as you do in second-order theory, because nothing happens. In second-order theory, the tidal forces are trivial at the horizon. You only get high tidal forces near I=0. In this case, maybe, and there are theories that try to replace the interior of a black hole with vacuum. Mazur and Motola, you may have heard of those, but in order to keep that together, they have to have another shell with where all the mass is concentrated to keep the vacuum from expanding. There's also Dibnikova that try to basically again do the same thing. As you try to go near R=0, your equation of state changes. Instead of P=3 rho, becomes P=-3 rho or minus rho, and therefore you avoid the singularity theorems. The only thing I can see is that, but of course, all those solutions still have problems with evaporation of the black hole because you have a horizon. So the question here is it possible that for some theory, I don't know if this theory or some other one, maybe R² theory, which I understand is only globally conformal invariant, to avoid having a horizon. And the reason we have horizon is because God has given us G in the Lagrangian, and if you take G with a lot of mass, then you have another mass scale, which is the Schwarzschild radius, and you can see that the geometry changes from time-like outside to space-like inside, and of course, then you end up hitting a singularity. But I agree with you, all those issues that maybe have to be resolved. But if we don't have this fourth order theory,
they have been resolved.
They have been.
That's the way they are.
They have not. No, they have.
Maybe you want to discuss that.
Yes, maybe we'll discuss the
yes,
in private. Yes.
We may want to come to your office and discuss, John.
So, what about the binary problem? I mean, have you tried to derive any post-Newtonian?
What binary? Binary black holes?
No, binary systems. So,
Two-body problem.
Two-body problem. So,
Yeah.
post-Newtonian approximations from the theory, because then there are infinitely more things that you can compare your theory with. I mean, for instance, if you have a thing like a variable G, for instance, then you would get something like a
Variable G, of course, they will change all the.
secular change in eccentricity, for instance, in the binary system. Or you will get things like dipole radiation.
I haven't thought of that. Well, that's what you guys should do. I'm too old. Yeah.
Quick question. So, does your gravity theory say something about the tension of the Hubble constant?
I can give you a reference that claims to have resolved it by Meir Simon. It's a guy in Israel. He claimed, I haven't really read the paper in great detail.
How exactly?
I don't know him, how he does it, but there's if you use his name in Astrophysics, you'll find several papers that he has. I talked to him in person, and we sort of agreed that conformal invariance is important. And I didn't read his paper that he claims he resolved the how do you call it, the Hubble tension. Now, if your G is variable, maybe that is a way to resolve. That's a way to resolve it. Now, why we end up with second-order theory instead of fourth, I do not know the answer to that. But it's a different way to start thinking about, because if you stick with Einstein, you end up with dark matter and dark energy. And I hear recently that the DAISY said that dark energy is decaying. So in order to explain now the late universe, we have to start reducing the dark energy. And what that means, I don't know. So a part of the two parameters are, well, one for the universe and one for its galaxy is not enough to resolve the issue. You need to have a decaying dark energy also to resolve the cosmology.
Yeah, it becomes an epicycle. Yeah.
Yes, then maybe it's worth doing something totally drastically different.
Okay.
Okay.
And
Dimos is
finish.
going to be here. Any questions? Further
No, I have
questions you can discuss.
a
with
question
him
for,
through
no,
216, right? Okay, let's thank Dimos again.
thank you.